Hey everyone, and welcome back to PrepFusion. So today we'll be starting the lecture 12B of linear algebra chapter. So in this lecture, right, lecture 12A and B, what we studied? We studied about vectors, vector spaces, linear span, and about the about rank also. Basically, we use the concept of rank to find the linear span, right? So basically, we are using the same thing over and again, but just with different names. Okay, so basically in this lecture we learned about basis vectors. What are basis vector? Dimension of vector space, null space. Okay, I have mentioned this name previously. Now we'll understand what does actually null space mean, and also few special matrices which I skipped over. But before starting this, I skipped few questions right in the previous lecture, so we will try to do this. Also, I'll try to quickly summarize what we learned in the previous lecture. So let's quickly summarize. Basically, we started with vectors, right? What are vectors actually? So vectors are nothing but row matrix or column matrices. Basically, we have to put all the data, whatever data we have in this real world, like the position data, right, or speed data, all like velocity has its direction and speed. Okay, so basically all this data we have to put it in the computers. Now in the computers we generally use matrix format. Okay, if you have ever learned programming language, you will know there is a data structure known as arrays. So we use matrix format to store data. So if you want to store that data, so we have to use this matrix format. So we convert this vector into matrix format and store this in the computer. So that's why this is very important to understand how is this written like vectors in linear algebra is like this. Okay, and with this we do few calculations, mathematical operations to find our required solution or required result. Okay, analysis. So I hope you got the point. Basically vectors are column matrix or row matrix in this case, right? So now what a set of vectors? Set of vector means similar items. We have similar items over here, right? Similar items. So similar items means same dimension and they are stored in a set, right? So that's why they are called a set of vectors. Now then we come to the point. Now this was linearly independent vectors. Again, linearly independent. Again, the columns are linearly independent to each other. Basically they are not dependent, right? They are not dependent. Okay, that's why basically you can, this B can't be written in terms of this A, okay, or this C can't, if A, B, C are mutually linearly independent to each other, this A, B, C can't be written in terms of each other, right? Okay, so yeah, this was about this. So here I told you the condition for linearly independent vectors. This was the condition, right? So first I told that if they are linearly dependent, sorry, this is for the linearly dependent vector, sorry. So if they are dependent, that means I can write one of the vectors in terms of the other two if one is dependent. So then I derive that this is the final condition I get, and this is what you see in the books everywhere, right? So this is basically the condition that if three vectors are linearly dependent, then a linear multiple will be multiplied with them, and the summation of those three will result in zero. So if the summation is resulting in zero, then they are linearly dependent. But the thing is, this lambda 1, lambda 2, lambda 3 can't be all zero at the same time. Simultaneously they can't be all zero. Okay, so yeah, that is the case. Then we did few examples and we did few questions, right? So yeah, here I told you that determinant has to be 0, rank has to be less, right? So these are the few things. And how to find this dependency, I told you, right? How to find this determinacy? Basically from rank. Everything comes from rank, or you can directly do it through the determinant. If the rank is lower, then definitely that they are dependent. These three columns will be dependent if the rank is lower than this order at n cross n. Okay, so now we learned about vector spaces. Vector spaces are also set of vectors itself, but having a common property. It is covering a space. In this case, it is covering one dimension, x-axis it is covering, right? In this case, now here this is the notation of standard vector spaces. These are standard vector spaces where R means all of the elements inside are real elements, and n means dimensions. N is dimension, R means real. Okay, real n dimensions. 1D means only single line, single number line. 2D means over the whole surface area. Okay, over the whole surface area, xy. 3D means over the whole volume, okay, and like this it can go on, okay. So this is about the vector space in 2D. Okay, so this is a standard notation for vector space in n dimensions. You can either write in row format or in column format. Both mean the same thing. Okay, they don't mean anything different. Okay, here few axioms are given. These are theoretical thing, so I won't go into this much deeper, right? So I told you how to do vector operations, how to do subtraction, addition, all these things I told you. Now we learned about vector subspace. It is also a set of vectors, it is also a vector space, but it is a smaller vector space than of the bigger vector space. So if I can draw a Venn diagram, right? This is my V, right? This is my V, okay, and this is my W. So my W is lying within this vector space. Both are vector space itself, but W is a smaller vector space, right? W is a smaller vector space of this whole vector space V. Okay, it has to satisfy particular conditions. What are those conditions? Like x plus y equals to 1, x plus y equal to z, or x, y, z equals to 1, all those things. And if W is a vector subspace of V, we denote it with this symbol, like this right angled U, right? So U, W, U, or this whatever this is called, I don't know, V, right? So W is a subspace of V. Now we did a question over here and we understood like the meaning of subspace. This is covering the whole 3-dimension space R3. V is covering the whole 3-dimension space, but W is only covering 3-dimensional space, but the components, right? Component multiplication should be equals to 1. Okay, multiplication should be equals to 1. Okay, x, y, z should be equals to 1. So V is R cube, right? So this is 2 alpha 1, alpha 1, 2 alpha 2, alpha 2. Okay, so V1 R square x plus y 1 minus 1 minus 1 1. Okay, so we did this question, right? Which one is vector subspace and which one is not vector subspace. Then we understood the concept of linear span. This is very important. So basically, what does linear span mean? Basically, it is a linear combination. Okay, that lambda 1 x1, lambda 2 x2, all those things, right? It is basically the linear combination of this x, all the linear combination of x. If I put it in a space, then it is known as span of x. This is also a vector space itself, but it is a set of linear combination of all the vectors in vector space X. Whatever vectors are here, so this is the combination of all the vectors, right? So we got this point. Then I told you about the terminologies. I hope you got that clear. That if it is written that X is spanned by V, X is spanned by V, that means spanned by V. So all the combinations of V are can be written in equals to x1, right? X. Now V spans X. So all linear combination of V is spanning X. That is, all the linear combination of V is spanning X. Here V is spanned by X. So all linear combination of X is spanning V. X spans V. So all linear combination of X is spanning V. V is spanned by whom? X, right? So we'll do the linear combination of X. X spans V. So X means what? X is spanning V. So all the linear combination of X. So like that you can remember linear combination of X. Okay, the other one will go onto the left hand side. Then the other cases, right? So X belongs to linear span of V. So it is a linear span of V. You get attentive. What is linear span of V? Linear span of V means all the linear combinations of V. You write that. Then on the left hand side, what is left? X. So X belongs to the linear span of V. So X is equals to the linear span of V. Okay, like this you can understand. V belongs to the linear span of X. So what is the linear span of X? Linear span of X means all the linear combination of X, right? X1, X2, X3, which belongs to V. So you write like this. You remember like this. You just first decode the linear span part, then you write the other one on the LHS. Okay. So this is how you understood this is how I understand the concept of linear span. Okay, now this is V1, V2, V3, right? So I gave you one like example and we solved this question, right? We solved this question that what is actually, how to find out the linear span, basically. How to find out the linear span, we got this. Okay, then we solve the system of equations, need to be consistent for us to get a proper solution. Now for all values of x, y and z, this rank has to be equal to each other. Then only I will get consistent set of solutions. And if I get consistent set of solution in this equation, that means these are valid. Okay, this like this, there exists some alpha 1, alpha 2, alpha 3. There exists some alpha 2, alpha 3. If there exists some alpha 1, alpha 2, alpha 3 which satisfies this equation, then this will be called linear combination of v1, v2, v3 should be equals to x. Okay, now if this is true, then I can represent x. Okay, I can represent x, all of this. So with linear combination of x, will I be able to produce this v? Sorry, 1 second. Okay, I actually wrote one thing wrong over here. Linear combination, this should be linear combination of v, okay, and vector space x. Okay, this was wrong by me. So basically, does vector b spans v spans, right? So this will be the linear combination of v spans vector x. So x will be here on the LHS. Okay, that was my mistake. I wrote here correctly linear combination of v v1 v2 v3. Okay, but here I wrote it wrong, so my apologies. I was meaning something else and I was writing something else, so that's why I think the mistake may have occurred over here. So yeah, this was basically one mistake I made. So it should be with linear combination of v will I be able to produce vector space x. Okay, so yeah, this is the case. So we solved it and we got the equation, right? So let's now solve this example over here. So again we have v vector, okay, and v1 v2 v3, and x is a vector space of 3 dimension. Okay, does vector v spans vector x? So again the same meaning, right? So does vector v spans vector x? That means linear combination, again the same thing. I'll just copy and paste. Combination of v will I be able to produce vector space x. Okay, okay, so yeah, this is the case. Now basically what we have to do again, right? We'll do this same thing, right? We'll do this same thing, that is alpha 1 v1 alpha 2 v2 plus alpha 3 v3 should be equals to my x, right? So I can expand this. v1 equals to 1 minus 1 0 plus alpha 2 equals to 2 0 1 plus alpha 3 into 1 2 3. Okay, equals to, so this is equals to xyz. Now again we'll write this in the matrix format. This you don't have to do always, just this is a starting point, that's why I'm doing this always. Okay, basically so x is xyz only, because x, y and z all are real numbers, right? X, y and z all are real numbers. Okay, so basically what we'll do, we'll write this in the like matrix format. I can write this in the equation format. So basically alpha 1 first row, I'm equating the first row, alpha 1 plus 2 alpha 2 plus alpha 3 equals to x, then minus alpha 1 0 into alpha 2 into 2 plus 2 into alpha 3 equals to y, alpha 3 equals to y, then 0 into alpha 1, so this will be 0 into alpha 1 plus alpha 2 plus 3 alpha 3 equals to z, right? 3 alpha 3 equals to z. Again this is a system of equations. So again what I will do, I will again write this in the augmented matrix format. So basically either I need rank of A equals to rank of AB for consistent solutions, right? The same thing, why? Because I need valid values of this alpha 2 alpha 3 alpha alpha 1 alpha 2 alpha 3. If I don't have valid values of this alpha 1 alpha 2 alpha 3, how will I able to write this equation? I need the valid values. If there are no valid values of this alpha 1, if there is no valid solution, then I will never be able to write this equation. If this equation is not valid, then this equation is not valid. If this equation is not valid, then I will not be able to write that linear combination of v will be able to produce vector space x. So linear combination of v will not be able to produce vector space x if I have no solutions. That's why I need consistent solutions. Okay, so this will be 1 2 and 1, this will be minus 1 0 2, this will be 0 1 3, and again the augmented matrix, right? This is the augmented matrix A B. Okay, now this is x y z. Okay, so this is xyz. So basically what, again, you convert this into row echelon format. I will quickly convert this into the row echelon format and come back. Okay, I converted this into the row echelon format. One thing was a mistake on my side. Basically the question, right, this should be actually here, right, this should be 1 over here. Like the previous case I messed up this thing, because in the previous question also I think this was 2 over here, which was actually wrong. This wouldn't be 2, this would be 1 actually. But still, like in this question the answer wouldn't have changed if this would have been 1 or 2, but in this question the answer would have changed. That's why like I had to change this. I just remember because the answer wasn't coming what I was expecting. So here this should be 1, that is my mistake. So the equations will just change. This 2 will become 1 over here and this 2 will become 1 over here. So the matrix, this 2 will become 1. So I just converted this into the row echelon format. Simply I added row 2 and row 1, changed row 2. So this will be 0, 1, 3. And if I subtract this, right, this will be 0, 0, 0 and z minus y minus x. Okay. So now the thing is, what is the rank of this? What is the rank of this? You might say, sir, this is row of 0. So rank of A is 2. That is for sure. Rank of A is 2. Now rank of A, B cannot be equals to 3 for consistent set of solution. For consistent set of solution, right, it cannot be equals to 3 for consistent set of solution. Okay, now if it is cannot be equals to 3, obviously this cannot go to 0. So if this goes to 0, then this whole row will become 0. Again the rank will be 2. So we don't I'm talking about the wrong thing. If this goes to 0, then the rank will be 3 for this augmented matrix. So we don't want it to, we don't want, we want it to go to 0. We want it to go to 0 to make the rank 2. So we want it to we want the rank AB to be 2. Hence we have to make this 0. Z minus y minus x has to be equals to 0. So x plus y equals to z. Okay, for x plus y equal to z, we'll have valid solution. Only for these condition we can linearly combine v. Okay, for this condition. So let me write, only for x plus y equal to z we can linearly combine v vector and basically combine the v vector and what was it, produce vector space x, produce a subspace, vector subspace, vector subspace of x. Okay, so we will not be able to produce whole of the vector space. We will be able to produce a vector subspace of x. Hence we can say that v does not completely span vector x. Basically v does not span x. So this will be our answer. V does not span x. Does not span x. Okay, so this is our answer for this question. So now we'll go to the next question. Okay, so let's do this next question. So here we have a question where we have been given a vector space of 2D, right, 2-dimensional real vector space, which also has a condition. So this is basically subspace of 2-dimensional real vector space, which has this condition that x plus y must be equals to 0. Now it is written that x is another vector space of these two vectors. Okay, now it is saying that does x span v. Okay, does all the linear combination of x will span v. Okay, so let's do this basically. So how will you do this? So in this case, right, in this case we have a condition over here, so we have to take care of that also. So first let me do one thing, that our v is what, v I can rewrite like this, right, v I can rewrite like this, that it is r square r square which will be equals to x and minus x. Okay, x and minus x. So basically x plus y equals to 0. So x is equals to minus x itself, where x belongs to all real numbers, right? X belongs to all real numbers. So this is what my r is, right? R is a set of these vectors. Okay. Now I have to find out that whether with the linear combinations of this I am able to satisfy this condition. So what I will do, I will directly write that matrix, right? Directly write that matrix. Okay, A B augmented matrix. If I write the augmented matrix directly, what I will get? So this will be simply first column. Okay, this is written in the row format. I will write this in the column format, or you can write this in the row format as well. But I will write this in the column format. So this will be 1 minus 1 and then minus 1 1, right? Minus 1 1. Okay. So here what do we have? We have x and minus x. Okay. Now again let's convert this into the row echelon format. So this will be minus 1 0, this will be 0 0, and this will be 0. Okay, and this is x, right? Because what have I done over here? This is equivalent matrix. I have just added row 1 with row 2. Row 2 is changed to row 1 plus row 2. Okay, so this will become, so basically this is a whole row of 0, right? This is a whole row of 0. Now if this is a whole row of 0, then what is the rank of this? The rank of this is, rank of A is always equals to rank of AB, is always equals to rank of AB. Okay, is equals to 1, which is not our concern. Our concern is this, right? Our concern is this, that rank of A and rank of AB should be equal for our solutions to be consistent. So this is for all x. Okay, all x belonging to real numbers for any values of x. It doesn't matter because this row is always completely 0 for any values of x. Okay, rank will be always 1. Rank will be always 1 for this whole matrix. Rank A, augmented B, and only A, right? Only A also rank is 1. So it doesn't matter, we're getting infinite solution, that is fine, but this is always satisfying. So basically this question is correct. It is asked that does x span V? Yes, x spans. Yes, x spans V. What does this mean? This means that with linear combination of x, right? With linear combination of x, I will be able to write V. I will be able to write V, right? Okay. So let's go to the next question. The next question is, let V equals to 1 2 3 3 2 1. So V is a vector space of these two vectors. For which value of lambda the vector x belongs to linear span of V. Okay, linear span of V. So linear combination of V, I'll be able to write my x. With the help of linear combination of these two vectors, I will be able to write my x. Okay, so how will I write it? So basically, what is this asking? That x is spanned by V, or V spans x. V. So the wording is very important. V spans x. Okay, V spans x. So let me again use the same formula. I will directly write the matrix this time. I won't waste time. So once we know the concept, basically we have to write the matrix in column format, right? So we have to use these two vectors. So these two vectors are here, 1 2 3 and 3 2 1. Okay, and what else we have? We have 1 lambda minus 6 minus 2. Now anyways, lambda minus 2, right? So anyways, the rank of A, this rank of A will always be 2, right? Because number of columns is 2, number of rows is 3, but number of columns is 2. So rank of A will be 2 anyways. Rank of A will be 2. Hence, rank of A, B cannot be equals to 3. It has to be equals to 2, right? For consistent set of solutions. Consistent okay, for consistent set of solutions. Now just hold on a second. So basically the rank of AB has to also be equal to this. So either you can convert this into the row echelon format. What you can do is you can make this determinant of this whole matrix, right, equals to 0. That also you can do. Okay, because you have to make this 3 rows dependent with each other, then only one complete row will be 0, right? One complete row will be 0, then only determinant will be 0, then only we will be able to say that rank of AB is 2, right? Rank of AB is 2. Okay, or you can convert this in the row echelon format as well. So let's do it in both ways. First let's convert in the row echelon format, and then I will make the determinant equals to 0. So let me convert this in the row echelon format. So equivalent matrix will become this will be 1 3, this will be 1, this will be lambda minus I'm subtracting 2, right? So if I'm subtracting 2, this will be 8 0, this is minus 4, this is 0, I'm subtracting 3 9, and this will be minus 8, and I'm subtracting 3 with this, so this will be minus 5. Okay, so what I will do, I'll subtract these, right? Subtract again. This will be 0. I'm just subtracting 2 times this, right? So if I subtract 2 times this will be 16 plus 5, 16 minus 5, which is basically how much is it? 2 times I'm subtracting 16 minus 5, 11. 11 minus 2 lambda. Okay, 11 minus 2 lambda, right? So basically what needs to happen? My rank of AB needs to be 2, right? So for my rank of AB needs to be 2, this whole thing has to be 0, whole rows of 0. Okay, so I need to have the third row as rows of 0. So 11 minus 2 alpha should also be equals to 0. So it's not alpha, lambda. So lambda will be equals to 5.5. From here also you can solve, or what you could have done. Okay, this is basically the method 1. Okay, using Gauss elimination technique. Gauss elimination technique. Okay, method 2. Method 2 is basically using what do you say? Method 2 is determinant, right? Determinant of A slash B equals to 0, right? So basically what I will do, I will just directly copy this matrix and directly find the determinant of this. So like what you can do, you can directly calculate, right? So this is 1 into 2 into minus 2 minus lambda plus 6, and this is minus 2. I'm going along this column, right? So the minus 2 into 3 times minus 2, 3 times minus 2 minus of this 1, right? Minus 1. Now plus 3 times this and this, right? So this is 3 times lambda minus 6 minus 2. So this is minus 4 minus lambda plus 6. Then this is minus 2 times minus 6 minus 1. So this is minus 7. And this is plus now this is, what do you say, this is where was I got lost somewhere. So this is like, okay, where was I? Plus 7, okay, yeah. And this is 3 times 3 lambda minus 18 minus 2, which is minus 20. So all of this should be equals to 0, right? All of this should be equals to 0. So let me go into the next slide. So minus 4 plus 6, this is minus 2, not minus 2, sorry, plus 2, plus 2 minus lambda, then plus 14, okay, then plus 9 lambda, then this is minus 60 equals to 0, right? So this is 8 lambda is going over that side, so this is 46 minus 2, 44, okay. So if I, am I doing this correctly or not? So yeah, 44, 8 lambda, so if I divide by, this is 2 and this is 11, right? If I divide by 4, this is 2 and 11, so lambda will be equals to 11, or what, so not 11, will be equals to 5.5. Or what you could have done, you could have simply made these two rows 0, and from there you could have easily find out determinant, right? Like you would have got the same equation expression itself. Basically this minus 4 into 11 minus 12 lambda into this equals 0, so you will get the same expression again. So yeah, this is the answer to this question. Now let's basically start our new topic. So let's start with our lecture, that is lecture 12b. So let's first understand what does basis vectors mean. So basis vectors in physics, we have already learned this, right? So let's say I have a v1 vector. This is also a vector space. Okay, v1 is also a vector space of I cap j cap. Now x1 is also a vector space of combination of I and j, right? Combination of I j, all the combination of I and j. Basically this is a r square. So can you tell me that with this two combination, can I write this whole vectors, right? All of the vectors, each of them, can I write those? Yes, I can, right? Because this is representing 2D vectors, I and j. So I and j are here. If I say this is x, this is y, right? So this is I and j. So these are 2D vectors, and with the help of this, these are what, I and j, I can use like make produce any vector, right? Any vector I can produce. Okay, just hold on a second, let me check if this is recording. Yeah, this is recording, fine. So I can produce any vectors with this I and j. So this is also a vector space, and this is also a vector space. But what is the difference? Difference is, in the first one, right, I have the number of vectors are much lower. Okay, only 2 vectors I have, right? Only 2 vectors I have, and here I have all the vectors, like this is like r square. So like, as I can say that this x1 is spanned by v1, right? Linear span, like linear span of v1 is equals to x1, because with all the linear combinations like 3 I cap plus j, 2 I cap plus 2j, all those linear combination of these two vectors, I will be able to form my x1 vector space. So what is the terminology said over here? So the terminology is set like this, that v1 is forming a basis of x1. Okay, v1 is forming a basis of x1. Okay, or v1 is forming the basis of x1, whichever way you want to say. So let's take another example. Now you are familiar with this, right? ijk. So this is 3-dimensional. So I can cover all the 3D vectors with the help of these 3 vectors, I cap, j cap, and k cap. With all these 3, I'll be able to cover this whole x2 vector space, right? This is also vector space, this is also vector space. The difference is with all the linear combination of this, I'll be able to cover all of the 3 dimension, right? So in this case, again, the terminology will remain same, just the names of the vectors will change, right? This will become v2, this will become v2 and x2, this will become v2 and this will become x2. Okay, so v2 is forming a basis of x2, v2 is forming a basis of x2, right? So what are the observations that we see? Like, when do we call a vector space as basis vector space? Okay, when do you call it? So if you observe correctly, these 3, right, the dot product of these 2, then these 2 and these 2, what is the dot product of these 2? The dot product is simply 0, right? Simply 0, because dot product is what a dot b is equals to magnitude of a into magnitude of b into cos theta, angle between the a and b. Angle between them is 90, so cos 90 is 0. So dot product between them is 0. Okay, and this is the outer product. Or what is the inner product? What is the similar product? The similar product between them is I dot I, which is 1. Similar product is 1. I dot I is 1, and dissimilar product is what? Dissimilar product I dot j, I dot k is 0. So this is the first observation that we see. So here I can say similar product I dot I equals to j dot j equals to k dot k, right? So I dot I equals to j dot j equals to k dot k equals to what? Equals to 1, because magnitude of I is 1. 1 times 1 into cos of 0. Cos of 0 is 1. So similar product is 1. Now what about the dissimilar product? Or like here it is 1, but generally the notation is it should not be equals to 0. Okay, it should not be equals to 1. Here it is not equals to 0. That is the main thing. It should not be equals to 0. Now if I write the dissimilar product of these 3, I j equals to I dot j equals to j dot k equals to k dot I equals to 0. Okay, so it is equals to 0 over here. It is equals to 0. So the dissimilar product will be 0 and the similar product will be non-zero. So that is what is written over here. Okay, so basically what does this mean? Dissimilar product equals to 0 means it is set of mutually orthogonal vectors. If you remember correctly, right? If you remember what we discussed over in the orthogonal vectors class, right? Just in the previous class, dissimilar product equal to 0 means set of mutually orthogonal vectors. Right. Also, for it to be like orthogonal, the similar dot product should also be not equals to 0, right? So these two conditions has to be satisfied. Now if these two conditions are satisfied, that means like if a set of vectors are mutually orthogonal, then they also are linearly independent vectors. So these set of vectors are linearly independent, right? So they are linearly independent. Let me write here linearly independent vectors. Okay, so this is what like orthogonal means. So this is what we observe, right? So basis vectors are basically set of orthogonal, mutually orthogonal vectors. So the inner product is known as A dot B, but like I was talking about vectors. Now for matrix we have already done this, okay, but still I'm again explaining you, like we already learned this during the orthogonal vectors topic. So with matrix, what we used to do? We used to do the first A transpose B. If I want to do A dot B in physics vector, then in matrix format I will do A transpose V, right? That will be my dot product. So let's come to the formal definition of basis vectors. So a basis is a set of linearly independent vectors. So orthogonal means linearly independent vectors that can be used to represent any vector within that vector space. So vector space R square. So I can represent with I and j, I can represent all the whole of the xy plane, right? Xy plane. I can represent whole of the xy plane. Now, a basis vector refers to a vector that forms part of a basis for a vector space. Now, a basis vector refers to a vector that forms part of a basis for a vector space. So, basically, it is forming a basis. Okay. So, this is also a vector space, right? This is also a vector space. This is a vector space, right? This is a vector space. And this is also a vector space. Okay, so these two are vector spaces, right? So this is also what this is like this basis vector is a part of basis. So this basis vector space, right? This basis vector will be a part of this basis and will form a vector space, right? That forms for a vector space. So this thing is total basis vector space, and the individual vectors in this are known as basis vectors, right? Like this I cap is known as a basis vector, the j cap is known as a basis vector, and this whole thing is known as basis vector space. This v2 is known as basis vector space. Okay, so I hope you got the point. Now if b is basis vector space of v, then what we can say? Then b equals to b1 b2 up until m should be set of linearly independent vectors, right? So what are the condition for a vector space to be a basis vector space? We are coming to that. So as they should be orthogonal, that means they should be linearly independent vectors. That is the first thing. And also v is spanned by b. So all linear combination of b should be equals to v. Okay, all the linear combination of b should be equals to v, as we saw, right? So basically with I and j here, I and j, where did it go? Can I cover all of the xy plane? Yes, all of the linear combination 5i plus 6j, 4i plus 3j, all of the linear combination I can cover the whole xy plane. Just hold on a second, I have to pick up a call. Yeah, sorry for the interruption. So yeah, as I was explaining, it has to satisfy these two conditions, like they should be linearly independent vectors and v is spanned by b. These two should happen, right? Now steps to check for basis vector. What are the steps to check for basis vector? So you have to check, like what are the things you have to keep in mind while checking whether this vector space is basis vector space. So I should write basis vector space. Okay, how will you check? So let's do it with the example, and from there we'll directly understand how to check whether a vector space is a basis vector space. So we have been given this vector space, okay, and we have to check whether this is a vector space of this 3-dimensional 3D real vector space. Okay, so we have to check. So how to check? First we have to check whether they are linearly independent vectors or not. So how we used to check? Okay, either with rank or you can use the determinant thing. So here we have 3 vectors, right? So the rank should be equals to what? Rank should be maximum, that is 3. Even if the rank is less than 3, okay, then the columns or the rows might be linearly dependent with each other. So here I have B, okay, and I will form the matrix. Basically matrix is 1 2 3. Okay, I'm writing in column format itself. Okay, I'm writing in column format 3 to 1, then 2 0 1. Okay, now what is the determinant of this? So if you want to check the determinant, or you can convert this in the row echelon format, from there also you can solve. Okay, but I will do it with the determinant method, whichever is suitable to you. Determinant should not be equals to 0 for rank of B, should be equals, for rank of B to be equals to 3, full rank matrix basically. So basically this determinant equals to this 1 3 2. So I will do what? I will subtract 2 times the row 1 from row 2. So this will be 0, 2 times this will be minus 4, and 2 times this is minus 4. Okay, and I will subtract 3 times this, which is 0, 3 times this is minus 8, and this is minus 5. Okay, so basically what will be my determinant? So determinant will be 20 minus 32. So determinant will be minus 12, which is not equal to 0. Hence my rank of B equals to 3, right? Rank of B is equal to 3. That means that all of these column vectors, right? These column vectors, or you can write this in the row format also, doesn't matter, because determinant of A transpose is same as determinant of A. Rank of A transpose is same as rank of A. Okay, it doesn't matter. Now, but it is a full rank matrix. That means the 3 columns or 3 rows are independent. Okay, hence we can safely say we have passed our first test, that B vector space, let me color this in different, B1 B2 B3 are basically linearly independent vectors. Okay, linearly independent vectors. Okay, so yeah, these are linearly independent vectors. Now we have to go to the step 2. Now step 2 is what? We have to check if B spans X. Basically all the linear combination of B can I can find X, right? I can get back X if with all the linear combination of B. So for that again we will use the rank concept, but this time my X will be what? X is 3D, right? X is basically 3-dimensional real space. So X is 3-dimensional real space. That means I can write my X like this: X, Y, Z. Okay, where my X, Y, Z are all real, right? X, Y, Z are all real. Okay, so basically now what I will do? Basically my A matrix will be this, right? So A matrix is same only. So this 1 3 2. Okay, I will write this in terms of this, like just hold on a second. My B matrix is that. Let me write this A matrix as a whole itself, or else this will be difficult. Wait a second, let me do one thing. Let me write this B matrix, and this I can write as X matrix, right? X. So this is 1 3 2 2 2 0 2 2 0. Then what I am doing, I'm just doing the spanning condition, linear spanning condition, whatever we have learned in the previous lecture. 3 1 1, right? Okay, now this is XYZ. Now what should be the condition? The condition is basically our system needs to be consistent. Okay, system consistent. Okay, so yeah, this is the case. So basically, so so basically now how will you check? So basically the rank of this b, right, rank of this b is anyways 3 always. Rank of this b is 3, so rank of this b x will obviously be 3, okay, for any value, for all value of x, y and z, for all value of x, y and z, it doesn't matter, okay, for any value of x, y and z, it will be 3. So they are equal, hence system is consistent. So hence system is consistent. So hence system is consistent. So so solution exists. Hence I can safely say that b spans x. B spans x. Now if these two conditions are satisfied, that means, okay, that means basically this is a basis vector space, right? This is a basis vector space, right? Hence basis vector space. Okay, so now let's read the key points. Basically, let's read the key points. So here b equals to 1 0 0 1. So this will always form a basis vector space of R square. What is this? This is simply like if you want to recall like a vector, physics vector, this is I cap, this is j cap. Okay, here, right, this is what I j k 1 0 0 0 1 0 0 0 1. So I know you already know this, but just to reiterate these things, right? So 0 0 1 always forms a basis vector space of v r cube, right? 3 dimensional. This 1 0 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1 always will form a vector space of v r to the power 4, 4D vector space, right? So like you can go on, but I just wanted to reiterate this thing. If this comes up in the examination, you can directly tick your answer. Okay, so this was about the basis vectors. Now let's come to dimension of vector space. What is the dimension of the vector space? It is basically the number of distinct vectors in a basis for v is called the dimension of v. Okay, denoted by dimension of v. Okay, what does this mean? So let's say v is a vector space. Now the vector space has a basis b, okay, and it has m elements, m vectors. It has m vectors. Now the number of distinct elements, it should be b actually, number of distinct vectors, I think it should be distinct vectors of b. Number of distinct vectors of v will be basically the dimension of v. Okay, so let's do it with example. Here the vector space is v r square. So 2D vector space, 2D real space dimension, right? So it has dimension 2. What does this mean? Here you can see for 2D this forms a vector space. How many distinct vectors I have? 2. So this will be 2 dimension. Now v r cube. So for v r cube I have 3 dimension. So if I have 3 dimension, then how many how many vector space I have? How many distinct vectors I have in the basis vector of v r cube vector space? 3, right? 3. Okay, so there can be other bases also, but for forming a basis there will be only 3 distinct vectors. Okay, so again you can do the same example for r raised to power n. It will be n dimension. Okay, so let's now study few properties about dimensions. So I won't give any proof here. Okay, just you have to remember this, and these are easy to remember. These are just simply the probability formula what you should learn. Okay, you can relate like that, you can take the analogy like that. Okay, just hold on a second, let me check if everything is recording or not. Yeah, everything is recording, fine. So what are the properties basically? V1 V2 are two vector spaces, then dimension of V1 union V2. Okay, if I include those two vector spaces and make one vector space, right? So basically if I'm including two vector spaces, let me say r to the power 4 and r to the power 3, right? So then what will happen, the dimension, individual dimensions will get added. Okay, then 3 plus 4 will get added and minus the dimension of V1 intersection V2. So what is the dimension of V1 intersection V2 in this case, right? Are there any common common intersection? There isn't, right? There isn't, so this will be 0, so it will simply become 7 because 3 dimension is something else, 4 dimension is something else, right? So that's why. So yeah, that is about this one. Now dimension of v r s to power n will be n, which already have been written previously. Dimension of null space equals to nullity, which I already told you about nullity previously, which is equals to number of free variables. So dimension of null space is equals to nullity. So what was the null space? I told you, right? The solution vector that we get from the homogeneous equation is known as the null space. I told you about it a bit previously. Now we'll do this even more in details. Okay, more in details. So what is null space basically? Null space is basically the solution vector of matrix A, right? Of homogeneous equation. So I can write, or simply you can say that solution vector solution vector of homogeneous equation, right? So basically we have to find null space of the following matrices. We have to find null space of the following matrices. So like with this example we will be able to understand what does null space mean. So basically it is a solution vector, so this will be my A matrix and I will write this in the homogeneous format, and basically the solution will be a null space and the dimension of the null space will be the nullity, or you can say number of free variables. We'll understand what does dimension also mean, right? So yeah, let's solve each of this. So first I will copy this, right? First I will copy this. So basically this is x1, x2, x3 equals to 0 0 0. Okay, 0 0 0, and we have to solve this. So what you can do, you can convert this in the row echelon format. Okay, whatever suits you, or you can directly solve this, whichever is easier for you. So let's basically solve this. So let me first find the rank of this. Let me first find the rank of this. So if I want to find the rank, so what I can do is, so let me first calculate the determinant of this. From there I will directly able to find the rank, whatever option you choose. So if this is like, if the determinant is 0, then there will be infinitely many solutions. If it isn't 0, then there won't be infinitely many solutions. Basically there will be only 0 solution. So null space will be only 0 vector, right? So no free variable. So this is 2 0 1 1 1 minus 1. So what I can do, I can add these two rows, right? And here I will get 2 zeros. So this is 4 0 1 0 1 1 1. Okay, this is recording, right? Yeah, 0. Plus minus plus minus plus minus plus minus. So this will be minus only, right? Minus plus. So this will be like minus 1 into 4 minus 2. So this is simply equals to minus 2, right? So my determinant is equals to minus 2. It is not equals to 0. Hence, like my rank will be rank of A will be equals to 3. Hence my solution X solution will be a null. Okay, so basically in this case no free variables, x equals to 0, y equals to 0, z equals to 0, or x1 equals to 0, x2 equals to 0, x3 equals to 0. No free variables, I don't have any choice. Hence my nullity will be 0. Now can you tell me what is the dimension of this? Can you tell me what is the dimension? This is basically null, right? This is basically null, right? So basically this is representing 0. Okay, so if this is representing 0, this means r raised to power 0, right? It is not written over here, it is written r square. So what is r raised to power 0? Basically what does 0 represent? It represents a point, right? It not even represents a point, it doesn't even represent a point, right? So it doesn't even represent a point. 0 represent nothing. So r raised to power 0, what is the dimension? Dimension is 0. Dimension is 0. For r raised to power 1, dimension is 1. R raised to power 0, dimension will be 0. So dimension is 0. That is from there also you can understand that nullity will be 0. So I can say dimension is 0, right? So yeah, that is basically what this means. So dimension of the null space is nullity. From there also we can understand that this will have no free variables. Okay, so let's solve this B part. This is not one, actually this is B part, one iPad. Okay, okay, so basically this again, right? This again we can convert this into the row echelon format, right? So if I convert this into the row echelon format, what are they? This will be 0, this will be, I'm subtracting 3 times, this will be minus 4, this will be again minus 8, 3 times is minus 8, yeah. So I'm subtracting 4 times, this will be 0, 4 times this will be minus 4, 4 times this 12, this will be again minus 8. Okay, so here we see, right, like these last two rows are dependent on each other, right? So just hold on a second. So I'm subtracting like this also, like okay, I'm not only doing operation on this, actually not on this. So like the determinant of this is 0, determinant of this A is 0, so hence we'll get infinitely many solutions, right? We'll get infinitely many solutions. Yeah, sorry for the interruption, actually my iPad got crashed. So like as I was explaining, right, so we will do these operations. Okay, we'll convert this into the row echelon format. So this is 1 2 3, this will be 0 minus 4 minus 8, this will be 0 minus 4 minus 8, and here I have the equation, right? X2 x3 x4, or you can write it like this: A augmented B, right? On the right hand side I have everything 0, on the right hand side I have everything 0, right? So this is A augmented B. Okay, so basically what I can say, like this, right? This, what will this become? This will be 1 2 3 0 0 0 0 minus 4 8 minus 8, this will be 0 0 0. Okay, so now basically what I can say, that my x3 can be any variable, right? X3 can be any variable. If I write this minus 4x2, I'm writing the with the second row equals to 0, so x2 equals to minus 2 x3, right? x2 equals to minus 2 x3. So I can write x3, equals to alpha 3. So x2 equals to minus 2 alpha 3, right? x2 equals to minus 2 alpha 3. So I have got one free variable. Now I will write x1 solution. X1 basically I will write along the first row. So x1 plus 2x2 plus 3x3 equals to 0. Okay, hold on a second. Equals to 0. So x1 equals to minus 2 into x2 is equals to minus 2 alpha 3. So this I can write minus 2 alpha 3 minus 3 x3 into alpha 3 basically. So x2 equals to x1 equals to 4 alpha 3 minus 3 alpha 3. So x1 equals to alpha 3 itself, right? x1 equals to alpha 3 itself. So let me write this in the solution format. So okay, am I doing everything correct or not? This is minus 2 alpha 3, right? Yeah. So this is minus 4, right? So yeah, this is minus 4 minus 2. Okay, am I doing this negative only? What did I do wrong? Anything I did wrong? I'm thinking like, did I do anything wrong? This is, I'm subtracting 3 times this, so this will be minus 8 only. Yeah, this will be minus 8 only. Yeah, correct only. So then I'm subtracting 4 times this, so this is 8. 4 times this is minus 8 again. Okay, fine. Yeah, this is correct. Okay, yeah, this will be minus only. So what will this become? So my solution vector, right? Solution vector will be x2, where is it? x2, x3 and x1 is 1. So it will be alpha 3 minus 2 alpha 3 and alpha 3, right? Minus 2 alpha 3 and alpha 3. So it will be equals to alpha 3 into 1 minus 2 1. Okay, so yeah, this will be the solution vector. So here what do you see? Okay, here what do you see? This is like a I can like cover this whole space, right? So now how many free variables I have? So free variables I have 1, right? 1. Now how many solutions I have? Only one linearly independent solution, right? Only one linearly independent solution. Okay, basically this is the only one vector that is representing this whole 3D space, but I can only cover this in one direction, right? In one direction, because I'm not able to cover individually this. Okay, individually these vectors I'm not able to cover. Okay, only I'm able to cover only one one line at a time. So what do I mean by this? So let's say I have a 3D space, right? 3D space x, y, z, and this is my vector. So what is this? This is 1 in the positive x direction, minus 2 in the positive negative y. Okay, negative y will be here, positive y, and z in the 1. So it will be somewhere around behind, right? So only I'm able to scale it. Okay, I'm able to only scale this vector along this direction only. Okay, along this direction only I will be only able to scale. I will not be able to move this in this direction or in this direction x, y, z. I'll only be able to move this in this one direction. That's why this is 1. That's why what is my null space? Null space is 1. I have only one independent, like let me go back to the definition here. So where did it go? Vector key point here. What will be the dimensional null space? Dimensional null space will be 1. Basically number of linearly independent vectors. So I can also write number of linearly independent vectors. Okay, so or you can find the basis of that, and from there also you can understand. So the basis of this vector, right, will be only this 1 minus 2 1. The basis of the vector will be only this 1 minus 2 1, because with this, right, I can represent this whole vector space. Okay, so with 1 minus 2 and minus 1 I can represent this whole vector. So I will only need one vector. So one distinct vector is enough for me to represent this whole space, because this is only representing this line. So if I take 1 minus 2 1 as a vector, that will be my basis vector, because multiply 2 with it, multiply 3, multiply 4.5, multiply 3.5, that will be able to cover this whole vector space. Okay, that's why the dimension is 1 in this case. So this is the null space, and dimension is basically 1. Okay, dimensional null space is 1. Okay, so I will need only one independent vector, the number of distinct independent vector in a basis. So 1 minus 2 1 can become a basis, and with the help of that I'll be able to cover this whole vector space. What is the vector space in this case? This line, right? This line is the vector space. Only this line, right? This line. Okay, not this whole 3D space. My vector space is not R cube, not R cube. Just this line is a vector space, because I'm just scaling it. I'm just scaling this vector, right? Okay, I hope you got the point. So let's take the third example. From there you will understand better. So third example is this. So again I'm doing the x1, x2, x3. Okay, from the starting itself I can see the rank is less, right? Rank will not be equal, because rank is equal to 3 and highest rank can be 4. Okay, but let's see another thing. So this is 0 0 0. How many free variables we will have this time? I will have, let's see how many free variables we have. So let me again convert this into the row echelon format. So this is 1 1 1, this is 0, this is 1, this is 2, this is 3, this is 1, this is minus 1, this is minus 3, this is minus 5. Okay, so this is minus 5, right? So and okay, I have to, okay, I did a mistake. I should subtract 2. Okay, I did a mistake. So 2 times this 0, 2 times this is minus 2, this is minus 4, this is minus 6, and this is x1, x2, x3, and this is equals to 0 0 0. Okay, so this is the equivalent matrix. So what I can see is I can simply multiply 2 and then add with this, right? So this will be a whole rows of zeros, 0 1 2 3. This will be 0 0 0, right? And this will be x1, x2, x3, right? So basically how many free variables I will have? I will have 2 free variables, right? I will have 2 free variables. Okay, so if I write this second equation, right? So this is x2 plus 2x3 plus 3 x4 equals to 0. Okay, so what I can do is, like, x3 will be alpha 3, okay, and x4 will be alpha 4, because I don't have choice. I have to take anything, right? Take any values. So x2 I can write in terms of x alpha 3 and alpha 4. 2 alpha 3 plus 3 alpha 4. And what will be my x1? So x1 is equals to minus x2 plus x3 plus x4, right? So this is minus, now x2 is this, right? So what I can do, I can take the minus inside, so this will become plus. So this will be plus 2 alpha 3 plus 3 alpha 4 plus 3 alpha 4. Then what will this become? So then this will be plus x3. What is x3? X3 is alpha 3 itself, and we have a negative sign as well. So we have a negative sign as well. So this will be minus alpha 3 and minus alpha 4. Okay, so this will be alpha 3 plus 2 alpha 4. Okay, alpha 3 plus 2 alpha 4. Yeah. So how will my solution vector look like? So my solution vector will look something like this. So I can write my solution vector as this. So this will be simply what do you say, alpha 3 plus 2 alpha 4, and this is minus of 2 alpha 3 plus alpha 4, and this is alpha 3 and alpha 4. Okay, so this, how can I write? So this I can write in terms of alpha 3 and alpha 4, right? So this is this will be 1 minus 2 1 1. Okay, this will be plus alpha 4 times 2 minus 3 and 1 and 1. Okay, 2 minus 3 1 and 1, 2 minus 3 1 and 1. Okay, so now can you tell me, are these two independent with each other? Okay, can you tell me? They are independent, right? They are independent. They are basically two different vectors. Okay, if I write like this is like in the 4D space, I won't be able to draw, but what I am trying to explain is these two vectors are independent. So how much area can this cover? How much area can this cover? Think carefully. These two vectors are independent. How much area can this cover? They can cover a whole plane. Like previously, I was able to only go in one direction. Now I will be able to go in two directions. Okay, two directions. So these two directions can be able to cover this whole, like this is another vector that I will be able to scale, and this is another vector that I will be able to scale. And with a linear combination of these two vectors, I will be able to cover two, like one single plane, right? One single plane. That is why my dimension of null space are basically number of independent vectors. So in this case, my dimension of null space is equals to number of independent vectors. Number of independent vectors. Okay, so basically, what is my null space in this case? What is my null space? So here, what was my null space? In the previous example, my null space was this, right? My null space was this. Basically, it is the basis, right? It is the basis. So this was my null space, the solution vector basically. So it is 1 minus 2 1. Okay, it is my null space. Now in this case, what is my null space? This is equals to 2 actually, so which is equals to nullity. So what is my null space basically? What is my null space? So my null space is basically this. What was the solution basically? Solution was 1 minus 2 1 1, right? And another solution was 2 minus 3 1 1. Okay, so this is my null space. So here I have two independent vectors, and that will be my dimension of null space 2, right? Dimension of null space. So yeah, let's solve another question. So this, like, these are just basic questions. These may come up very rarely, these are asked, but we have to cover the topics. These are basically on the miscellaneous topics. So let x and y be 3-dimensional subspace of 5-dimensional vector space V. So they are each 3-dimensional subspace. Okay, so what will be the dimension of x and y? So dimension of x equals to dimension of y equals to 3. This is known. Now 3-dimensional subspaces of a 5-dimensional vector space V, of a 5-dimensional vector space V. Then smallest possible dimension of x intersection y. Okay, so basically we have to use that formula. So basically, what do you know? If I include dimension of x and y. Okay, if I include all of this, okay, like let me just write the formula. Dimension of x will be equals to dimension of x minus plus dimension of y minus dimension of x intersection of y, right? Dimension of x intersection of y. So this is the case. Now what can be the maximum possible value of this? What can be the maximum possible value of this? The maximum possible value of this is 5. Maximum value of this is 5, right? Maximum possible value of this is 5. So the maximum possible value of this is 5. Then what does this mean? This means that basically the maximum value of this is 5. So this has to be lesser than or equal to 5. At max it can be 5. So I can say, why is this maximum 5? Because if I take all the set of vectors, right? If I take all the set of vectors, okay, if I take these vectors and these vectors, so why is this 5? So here if I just show you one thing, let me take this x as I, j and k, okay, and this y as like I, j, k, l and m, okay. So these are 5 vectors in 5 dimensions, okay, but this has also dimension 3. So I can take this again, this k, right? I can take k again here, right? This is 3 dimensions, so this also has to have 3 dimensions, right? So k, l, m and I, j, k, k, l, m and I, j, k. So if these 3 are vectors, then what does this mean? Basically, what can be the with a linear combination of this, what can be my maximum dimension? So I can get I, j, k, l, m, right? I can get all the 5 basis vectors. So I can be able, I will be able to get 5 dimensions. That's why at max I'm taking, what does union mean? Take the both of them. I'm taking both of them and I can get at max 5 dimensions. That's why its dimension can be 5. Okay, at max. So basically, where was I? I was here, right? So dimension plus dimension of y minus dimension of x intersection y must be less than or equals to 5, right? So now we know dimension of x is what? 3. This is 3. So I will shift this to the right hand side. I will shift 5 to the left hand side. So if I shift 5 to the left hand side, so my dimension x intersection y is greater than or equals to this, right? Minus 5. So one, right? So it has to be greater than or equals to 1. So what is the question asking us? The question is asking us the smallest possible dimension. So smallest possible, what can it be? It can be 1. Smallest possible, it can be 1. So smallest equals to 1, right? So it has to be at least more than that. So here, what is the intersection here? You can see 1 dimension is smallest possible. At least one has to be same. All 3 can't be different. If all 3 are different, then this is like, what can be my v vector? So my v vector will be something like this, right? I'm just taking one example. I, j, k. I'm just doing this in rough. Let me do this. I, j, k, l, m, not m, right? lm, right? lm. Okay. So at max I can have 5 vectors and I have to pick 3 of this. I pick 3 of this, then I don't have extra vector. I have only 2 left. So I have to pick another one common from here. So at max at max I can at minimum I can have one common vector. Or what I could have done, I could have picked this 3, again I could have picked this 3. Okay, that is also a possibility. So what will my this intersection, dimension of intersection xy, it will be 3, right? It will be 3 because the 3 dimensions are same for them, xyz, sorry, not xyz, ij cap, the 3 dimensions are same for them. If you want to like find out from this equation, we can do that. So my dimension of x is 3, dimension of y is 3, fine. Now what is the dimension of x union y? It is again 3. Why? Because I am taking the dimension of x. What are dimension of x? ijk, yeah. And what is the dimension of y? ijk. They are same only. So I am talking the same thing in different manner, like not even in the different manner. They are same only. So dimension of x union y will also be 3 because they are talking the same thing, right? ijk, they are same only. So this is also 3. This is 3, 3. So 3 will get cancelled. I will only remain with 3. So dimension of x intersection y will be also 3. Okay, that will be also 3. So that's why that is the maximum value. Now, like you can do the other cases and you will be able to solve, right? I will not further explain this. Let's go to the next question. So this is the next question. Now, if the vector x, y, z form an orthogonal basis, so x, y, z are forming an orthogonal basis of 3-dimension real space. Okay, so ijk you can say, or 1 like 1 0 0 0 0 1 0 1 0. Then the vector w can be expressed as, okay, I wrote this wrong. I should write vector u. Vector u. So basically, I was talking about the general basis, but here this is also a basis vector, right? 3 distinct vectors I have, and if you check the condition whether they are basis or not, you can check, right? But what are they asking? They are asking that how can my u be expressed as a linear combination of the basis vectors? Okay, so basically what is this asking? Where did I go? It is asking that I will write my u in terms of linear combination alpha 1 e1 plus alpha 2 e2 plus alpha 3 e3. Okay, so u equals to 2 e1 minus e2 by 5. Oh, so okay, sorry, I was lost in some other thing. Sorry, we have to find the linear combination. So how will you do that? How will you do that? So basically, as we can directly write the equations. We can directly write the equations, right? What is the equation? So basically, I can write this. This u is basically minus 1 2 1 minus 1 2 1. This alpha 1 is basically 0 1 0, right? And this alpha 2 is what? This alpha 2 is minus 2 0 1, and then this plus this alpha 3 is 1 0 2 1 0 2, right? So basically what I can write like the first row I can equate, right? Minus 2 alpha 2 plus alpha 3 equals to minus 1. Okay, fine. Let's equate the second row. This is alpha 1 is only left, which is equals to 2, so that is good. Let's equate the third row. So this is 0, this is 1, this is 1. So again, this is alpha 2 plus 2 alpha 3 equals to 1. Okay, so basically now if I just want to find this, right, multiply 2 and then add. So this is 2 alpha 3, then this is 1, right? This is 1. So alpha 3 will be equals to 1 by 5. Okay, so alpha 3 is equals to 1 by 5, and alpha 2 will be, this is 1 by 5, so this is 2 by 5, this is 2 by 5, and this is getting subtracted over there. This is 3 by 5, so alpha 2 equals to 3 by 5. Okay, so am I doing this correctly? This is 1 by 5, right? Alpha 3 is 1 by 5, so this 2 times this goes over there, 2 by 5 minus, yeah, it will be 3 by 5 itself, right? Alpha 2 will be 3 by 5, right? So yeah, let's now basically write this, right? So like write this in the format. So basically what I can say is my u will be equals to where did it go? 2 times alpha 1 times e1, so 2 times e1, then plus 3 by 5 E2 plus 1 by 5 E1. Okay, E3 by 5 itself. Okay, so this is my alpha 1, alpha 2 and alpha 3, right? So where are the options matching? 2, 1 by 5 and okay, 2, 3 by 5 and 1 by 5. 2, 3 by 5 and 1 by 5. Okay, option B is basically matching, right? Option B is matching. Basically all of them are positive and this is 2, 3 by 5 and 1 by 5, right? So yeah, this is the case. So like these were the questions. Okay, if you want more questions, let me know. I will do more, take more questions on these topics. Just we have left few miscellaneous topics. One is about the rotational matrix. I haven't taught you what is a rotational matrix. Just nothing, just it rotates. Okay, it rotates along anti-clockwise direction. That is the rotational matrix. What do you mean by that? A rotational matrix can be defined as a transformation matrix that operates on a vector and produces a rotated vector. Okay, visually we'll understand this. I will tell you visualization. Okay, such that the coordinate axis remains always fixed. Coordinate axis will be fixed, just the vector will be rotated along a particular angle, okay, in the anti-clockwise direction. This matrices rotate a vector in the counterclockwise direction by an angle theta. A rotational matrix is always a square matrix. First important point. Okay, so I will highlight this. It is always a square matrix with real entities. So it would always have real entities. Rotational matrices are orthogonal matrices with determinant 1. So these are the properties of rotational matrices. They are orthogonal matrices with determinant 1, right? Okay, so basically rotational matrix will satisfy this condition that R transpose will be equals to R inverse. Also determinant of R will be equals to always 1. Okay, always 1. So let's understand the rotational matrix in 2D. Let me explain the rotational matrix in 2D. So rotational matrix in 2D will be like this. Okay, so basically xy is the coordinate. So at first I had some this xy matrix, right? Xy matrix. Now if I apply linear transformation with this, if I multiply this is the rotational matrix, then what will happen? This vector, right, will get shifted in the anti-clockwise direction. Okay, the magnitude will be same only, R only, but this will get shifted in the anti-clockwise direction with the angle theta, okay. Now for clockwise rotation, replace theta to minus theta. If I want to rotate in the clockwise direction, basically replace this theta to minus theta and this will be replaced to clockwise direction. Okay, so in the 3 dimension, I am just telling you a few examples of rotational matrix. So this you can, if you see in the examination hall this type of matrix, then you should be able to recall that this is a rotational matrix. Okay, so in rotational matrix in 3D you can see, right, the format will be something this, right? Format will be something this, right? This rotates in the counterclockwise rotation of gamma about the x-axis. Okay, here like I will rotate about along the x-axis. So this axis, right, I am rotating along the x-axis. Okay, what about this? This is rotating along the y-axis. Okay, the x and z axis are fixed. X and z will be fixed, right? Here x and z are fixed. Only I am rotating along the y-axis, right? So and this, right, this matrix will rotate along the z-axis where x and y will be fixed, right? So you can just remember few this matrices, right? These are standard matrices, rotational matrices. Also I have forgotten to tell you about the normal matrices. Okay, so what are normal matrices? So normal matrices are basically where it satisfies this like condition, right, where A conjugate transpose into A equals to A into A transpose conjugate. So like you might say, sir, this is something similar, we have already learned this. Yes, you have learned this. You have learned this, that this equals to I. Okay, that was for the condition of unitary matrix. But if these two are equal, but it is not equals to I, then this is known as the normal matrix. Okay, but if this is equals to I, then this is known as the unitary matrix. Okay, okay, so this is the difference between unitary matrix and normal matrix. So yeah, this is basically what we learned. throughout this lecture basically I taught you about the basis, dimension of basis, null space, dimension of null space, and few miscellaneous matrices, and we did question on null space also. Okay, so like this is a very short topic, not much questions come up from this, so that's why I didn't go much in depth into this. So like I covered all of the linear algebra, right? If you want anything, you can put it down in the comments below. I will be happy to help. Okay, and for me, like I hope you like this lecture series. Do let me know if you did like this lecture series. Do like the lecture series, okay? And do watch each and every bit of it, because I have tried to explain all of the concepts in a very detailed and concise manner. Okay, so yeah, I hope to see you in the next lecture. Thank you for watching.